What is the main motivation behind the proposed method in the paper?
The main motivation behind the proposed method in the paper is to reduce the total compute required for language modeling tasks by implementing a conditional computation technique called mixture of depths, MOD transformers. The goal is to dynamically allocate compute resources per token, per layer, in a transformer network, allowing tokens to either undergo computations, self-attention and MLP, or bypass them through a residual connection, thus saving compute when unnecessary. By using learned routing decisions, the MOD transformers aim to intelligently allocate compute resources only where needed, leading to significant efficiency gains, such as reduced memory footprint and fewer flops per forward pass. This approach enables the network to achieve equal or better performance compared to traditional transformers, while using a smaller total compute budget, ultimately improving hardware efficiency without compromising overall performance.
How does the proposed method aim to reduce total compute in language modeling compared to vanilla transformers?
The proposed method aims to reduce total compute in language modeling compared to vanilla transformers by implementing a technique called mixture of depths, MOD. In MOD, tokens are dynamically routed either to undergo computations in self-attention and MLP blocks or to bypass these computations through a residual connection, thereby saving compute. By limiting the number of tokens participating in each block's computations and using a per-block router to decide which tokens to process, the total flops per forward pass are reduced. The network learns to intelligently allocate compute by making decisions per token, allowing for a more efficient use of resources. Additionally, the MOD technique allows for a trade-off between performance and speed, enabling models to achieve equal or better results with a smaller flop footprint per forward pass. Overall, the MOD method optimizes compute usage by dynamically allocating resources based on the specific needs of each token, leading to significant efficiency gains in language modeling tasks.
What is the key difference between mixture of experts, MO, transformers and the proposed mixture of depths, MOD technique in terms of routing decisions?
The key difference between mixture of experts, MO, transformers and the proposed mixture of depths, MOD technique in terms of routing decisions lies in how tokens are routed within the network. In MO transformers, tokens are routed to one of many expert MLPs, while in MOD transformers tokens are routed either to undergo a computation, self-attention and MLP blocks, or to bypass the computation through a residual connection. This means that in MO, tokens are routed to different expert MLPs for processing, while in MOD, tokens are routed within the same transformer block to either engage in computations or take a shortcut through a residual connection. Additionally, in MO transformers, the total compute expenditure remains constant as tokens are routed to different experts, whereas in MOD transformers, the total compute budget can be reduced by limiting the number of tokens participating in a block's computations, leading to potential compute savings per forward pass.
Explain the concept of conditional computation as discussed in the paper.
Conditional computation, as discussed in the paper, refers to the technique of dynamically determining when and how much computation should be expended during the processing of tokens in a transformer model. The paper introduces the concept of conditional computation as a means to reduce total compute by allocating computation resources only when necessary. This is achieved by implementing a routing mechanism that makes decisions per token in each layer about whether to apply a computation, such as self-attention and MLP blocks, or to bypass it through a residual connection, thus saving compute. The paper presents the mixture of depths, MOD technique, where tokens are routed through different numbers of layers in the transformer, allowing for a trade-off between performance and speed. The MOD technique enables the transformer to intelligently skip unnecessary computations, leading to reduced flops per forward pass without compromising overall performance. Additionally, the paper discusses the importance of learned routing mechanisms in conditional computation, highlighting the significance of tokens dynamically choosing whether to participate in computations based on their context and the network's objectives.
How does the paper address the issue of dynamic computation graphs in the context of conditional computation?
The paper addresses the issue of dynamic computation graphs in the context of conditional computation by proposing a technique called mixture of depths, MOD transformers. Unlike traditional transformer models that expend the same amount of compute per token in a forward pass, MOD transformers dynamically allocate compute by making decisions per token in each layer about where to spend compute from the available budget. This approach allows for a static compute budget that is user-defined and unchanging prior to training, leading to hardware efficiency gains, such as reduced memory footprint and reduced flops per forward pass. The MOD technique enables tokens to either undergo computations in self-attention and MLP blocks or be routed around them through a residual connection, thereby reducing the total flops per forward pass. By implementing learned routing mechanisms, MOD transformers intelligently skip unnecessary computations, achieving equal or better performance with a smaller flop footprint. Additionally, the paper discusses routing schemes like token choice and expert choice routing, highlighting the importance of using learned routing decisions to determine token participation in computations, thus optimizing the use of compute resources efficiently.
What is the significance of setting a static compute budget in the proposed method?
Setting a static compute budget in the proposed method is significant because it allows for more efficient allocation of computational resources in language modeling tasks. By limiting the number of tokens that can participate in computations within a block, the method reduces the total compute required per forward pass compared to a vanilla transformer. This approach enables the network to dynamically allocate compute resources by making decisions per token, optimizing the usage of available compute. The static compute budget ensures that hardware efficiency gains, such as reduced memory footprint and fewer flops per forward pass, can be anticipated and exploited proactively. Additionally, the method allows for the preservation of overall performance while achieving computational efficiency. By implementing a static compute budget, the network can learn to choose the most relevant tokens for processing, leading to improved efficiency and performance in language modeling tasks.
Describe the routing schemes considered in the paper and their implications on model performance.
The paper discusses two learned routing schemes for conditional computation in transformers: token choice routing and expert choice routing. In token choice routing, tokens choose their preferred computational path based on per-token probability distributions, potentially leading to load balancing issues. On the other hand, expert choice routing involves each path selecting the top K tokens based on their preferences, ensuring perfect load balance but potentially causing over or under processing of some tokens. The paper opts for expert choice routing due to its efficiency in load balancing without needing auxiliary balancing losses, allowing critical tokens to be prioritized. This routing scheme helps determine which tokens need block computations, leading to compute savings by routing tokens around blocks, ultimately improving model performance by using fewer flops per forward pass. The routing decisions impact downstream performance, with the optimal model finding a balance between routing tokens around blocks and engaging with them, showcasing the importance of learned routing mechanisms in enhancing transformer efficiency and performance.
How does the paper handle the non-causal nature of the top K operation in autoregressive sampling?
The paper addresses the non-causal nature of the top K operation in autoregressive sampling by testing two methods to work around this issue. The first method introduces a simple auxiliary loss that affects the primary language modeling objective by approximately 0.2 to 0.3%, allowing autoregressive sampling. This method uses a binary cross-entropy loss where the router's outputs serve as logits and the top K selections of these logits serve as targets. The second method introduces a small auxiliary MLP predictor that receives the same inputs as the router but predicts whether a token will be among the top K or not in the sequence. This method does not impact the language modeling objective significantly and does not affect the step speed. These methods enable autoregressive sampling by routing tokens based on the router's output, which does not rely on future token information, ensuring successful sampling without compromising performance.
What are the key findings regarding the training methods and results of the mod transformers compared to baseline models?
The key findings regarding the training methods and results of the mod transformers compared to baseline models are as follows. 1. Mod transformers demonstrate the ability to achieve lower loss than baseline models while using fewer flops per forward pass, leading to faster training times. 2. By reducing the capacity of blocks and implementing learned routing decisions, mod transformers can outperform isoflop optimal baseline models in terms of performance and speed. 3. Aggressive capacity reduction, down to 12.5% of the total sequence, coupled with frequent opportunities for full capacity self-attention and MLP computations, leads to improved performance. 4. Learned routing is crucial for the success of mod transformers, as models using stochastic routing perform significantly worse than both the baseline and normal mod transformers. 5. The optimal mod transformer is the one that uses as many flops per forward pass as the isoflop optimal baseline, allowing for direct prediction of the optimal model size for a given training budget. 6. Empirical evidence suggests that adding depth rather than width to the model is more beneficial when adding flops, and the optimal capacity for mod transformers is determined to be 12.5% capacity blocks, every other block. 7. Mod transformers exhibit memory savings relative to equivalently sized baseline models at larger sizes, potentially requiring fewer total devices for training. 8. The integration of mod with MO models in mode models shows compounding performance improvements, with the integrated mode approach being more effective than simply reducing the capacity of experts in conventional MO models. 9. The routing machinery in mod transformers provides flexibility in adjusting the types of computations available to the network and their relative cost, offering a tool to tune a model's compute per forward pass and inference time. 10. Overall, mod transformers offer a promising approach to improving efficiency and performance in transformer models through learned routing decisions and reduced flops per forward pass.
How does the integration of mixture of depths, mod, with mixture of experts, MO, models enhance performance according to the paper?
The integration of mixture of depths, mod, with mixture of experts, MO, models enhances performance by compounding the benefits of both techniques. The paper discusses two variants of integrating mod with MO models, staged mode and integrated mode. In staged mode, tokens are routed around or towards blocks before the self-attention step, allowing for tokens to skip the self-attention computation when necessary. On the other hand, integrated mode incorporates mod routing by including no-op experts alongside the conventional MLP experts. This integration simplifies the routing process and ensures that tokens explicitly learn to choose the residual path around the experts. The paper notes that the integrated mode approach outperforms simply reducing the capacity of experts in conventional MO models and relying on token dropping for residual routing. By combining mod's token-level routing decisions with MO's expert-based computation routing, the integrated mode approach optimizes the model's performance by efficiently utilizing compute resources and improving the overall language modeling objective.